Hi folks, so we're going to continue our work on Unit 2, Lesson 3. So let's start by recapping what we saw last time. So we saw that we could group rational functions into three categories, and those had to do with the degrees of the numerator and denominator, and in particular how they related to each other. So if the degree of the numerator was smaller than that of the denominator, so for example, if you have something like x squared over x cubed plus 1, we reasoned out that when it comes to n behavior, remember that we're only interested in very large x values, so as x approaches positive infinity, or very small x values as x approaches negative infinity, that the denominator, in this case here, increased more quickly than the numerator did. So imagine you put in a billion into x, x a billion squared is very, very large, but it's almost negligible compared to a billion cubed. Okay, so the denominator starts to take over, and so as x gets larger and larger and larger, this is going to get closer and closer to zero, and similarly as it approaches negative infinity. And we're going to take this as being reasonable enough that we don't really need to justify it any further. All right. Now, similarly, we can use this idea when the degree of f is larger than the degree of g. So if we switch these around, now we have x cubed plus 1 over x squared. Similarly, here, even if you pick a very large x value, yes, the denominator will be large, but the numerator will be much, much larger. So again, we can say that this is going to approach positive or negative infinity depending on the sign of the function. All right? Now, when it came to when the degrees were equal, well, we had to do a little bit of reasoning here. So let's say we had something like x squared plus x plus 1 over x squared plus 3x minus 5. On this case here, we do use somewhat of a similar reasoning, that if we put in a very large x value, okay, it's the first terms that are going to take over the numerators and the denominators. So again, if you put in x equals a billion plus 1 is very large, but it's negligible compared to a billion squared. And similarly in the denominator. And the larger x gets, the more these terms that are not the leading terms become negligible. So slowly, slowly, it starts to look like x squared over x squared. And so eventually, this is just going to approach 1. And similarly, you can make an argument if this was 2x squared, say plus 1 over x squared plus x minus 1. Again, these terms here become negligible as x gets really, really large. So this is going to approach 2x squared over x squared. So it's going to approach 2. So in other words, a horizontal asymptote of y equals 2. And so we realized that all you had to do was look at the ratio of the leading coefficients. All right. So we are going to look a little more algebraically at this particular scenario. And we also saw that while we could reason out that when the numerator is a larger degree, it would approach positive and negative infinity. Well, we want to know whether it's approaching positive infinity or is it approaching negative infinity. And we saw that it seemed to do so in a very special way. So we'll take a look at that again later on. So next, we notice that we had these two functions here. So if we go back to Desmos, we saw that that function there was exactly the same as this function here. And if you look at the n behavior, it's approaching 1, y equals 1, horizontal asymptote, and that fits with what we saw because we've got x over x approaches the ratio of the leading coefficients. Okay, so what I asked you to do is to see if you could justify this algebraically. So first of all, we used some grade 11 math to show that these were indeed equal. Now notice here you had to know that they were equal to show this relationship. What I want you to do is see if you can use some grade 12 math to show that x plus 2 divided by x plus 1 is equal to this expression there. Look at how I wrote it. See if that gives you any hints, and then see if you can use this expression to justify the n behavior. So take about 4 minutes to work on that. All right, so we're back. So hopefully you thought, seeing this expression here, this looks a lot like a quotient plus a remainder term. And in fact, we can divide these two polynomials. And since we're dividing by x plus 1, we can use synthetic division. So let's do that here. Since we're dividing by x plus 1, our representative is -1. So the 1 comes down. 1 times -1, -1. 2 minus 1 is 1. So remember that this last number here represents our remainder, and this represents our quotient. And since there's only one term, it must be a constant polynomial. So here we have that x plus 2 over x plus 1 can be written as our quotient of 1 plus our remainder of 1 over the original divisor. Okay, so here we're able to show that we get that same expression. But now let's see if we can use this to justify the end behavior. So remember, end behavior is all about what's happening as x approaches positive or negative infinity. And so here, this portion, well, it doesn't change, it's just a constant, but this portion here starts to get closer and closer to 0 because the denominator increases, numerator doesn't, so the whole thing is just going to approach 1. Okay, so this more algebraically justifies the end behavior of this function. Okay, now we're actually going to consider another algebraic tool that we can use to justify the same thing. And you might ask, well, we already have one thing that works. Why come up with something else? Because it's a trick that, this might work well for certain circumstances, and the one we're going to see now might work in other circumstances. And again, it's about doing some algebra. Except here, what I'm going to ask you to do is, remember, this is a fraction. So what can we do to a fraction without, that doesn't change it? We can multiply numerator and denominator by the same thing, or divide numerator and denominator by the same thing. So I want you to take this expression and divide the numerator by x and the denominator by x. Now notice here that x is the highest power, x to the 1. I want you to then do the same thing with this expression. And again, divide by the highest power of x. And with what remains, can you justify what the end behavior should be? So here, notice we expect it to be approaching 3 over 5. Can you show that algebraically? So again, we'll leave you about 4 minutes or so to do this and come to a conclusion. All right, so let's come back and have a look at these here. So I've already divided numerator and denominator by x in this case here. And so now I can do some simplifying. So here I can distribute the division of x. And in the numerator, I'm left with 1 plus 2 over x. And in the denominator, I'm left with 1 plus 1 over x. And again, remember that we're interested in end behavior. We see that this term here is going to approach 0 as x gets very, very large. This term here is also going to approach 0. So in the end, as x gets very large or very small, the whole thing approaches 1. Okay, and now here we can do something similar. All right, divide both numerator and denominator by the highest power of x, and let's see what happens. Well, here we're left with 3x cubed over x cubed, 3, and I think you can see where this is going, because now each of the other terms is going to have an x in the denominator. Okay, and similarly in the denominator here, we're left with 5 plus 1 over x plus 1 over x squared. And all of these terms that are not part of the leading term all approach 0 as x gets very large or very small. And so what does the whole thing approach? Just 3 over 5, as we would anticipate. Now, by the way, if you wanted to, you could also divide these. In this case here, you'd have to use long division, and you would see that you would have a quotient of 3 over 5 plus a remainder term that approaches 0. Okay, so like I said, keep these two methods in mind. Okay, this one might come in handy when you have something that looks like a rational function but isn't quite a rational function. And the previous example where we used division, long or synthetic division, might come in handy, well, sooner than you think. All right, so let's go back to those examples where the numerator had the higher degree. And in particular, if you look back on your investigation, look at functions 15, 17, 18, and 19. Okay, we already saw that something very interesting happened. So I want you to do two things. Let's take a look at these here. I want you to consider what happens in these scenarios. So I believe it's this one here and then these three. Maybe you want to even graph them on Desmos. Compare the behavior, the end behavior of these functions, and take a look to see if you can find a relationship in the functions in the numerator and denominator. Okay, and then I give you a bit of a suggestion here. I say, think about doing a division to see if you can explain the end behavior. Now, notice I say long or synthetic division, but in fact, give you a bit of a hint here. If you look at these examples here, you don't really need to use either a synthetic or long division because they can just be divided by distributing the division here because you're just dividing by a monomial. Whereas this one here, you cannot do that. You will have to use, well, in this case here, a long division. All right. So step number one, what is the pattern that you notice between the functions in the numerator and denominator and the type of end behavior that you see? And number two, how might division help you to describe that end behavior? So we'll leave you about 7-8 minutes for this one here. All right, so we're back. So let's take a look at these functions here, and we had seen this before. So if you look at this one here, you notice that, well, can't really see part of the function. So when we zoom out, we see this function, end behavior clearly going to positive and negative infinity. But as we zoomed out, we saw that the end behavior seems to approach a line. Now, not a horizontal asymptote, but a slanted line. Then you look at this one here, and again, similar. This one here, similar. Then when we looked at this one here, we see it's still approaching positive or negative infinity, but it seems to start to look like a parabola. So hopefully you notice that there was a pattern here. If you look at this function here, that function, you hopefully notice that the degree of the numerator is not just larger, it's exactly 1 larger than the denominator. Whereas this one here, the degree is 2 larger than the denominator. Now, when we think about it, it kind of makes sense, because when you divide a quadratic by a linear, or a cubic by a quadratic, a quartic by a cubic, we know that the quotient is going to be the difference between the numerators and the denominator, between the dividend and the divisor. So here the difference, 4 minus 3, tells us that the quotient is going to be a linear function. Here, 3 minus 1, that the quotient is going to be a quadratic function. We just need to show that that remainder term is going to be approaching 0. So let's have a look at that. Now, by the way, if you look back at the notes, we could probably make an argument without calculating, but let's see what happens here. So here I've got a division by a linear, so let's use synthetic division. So here we've got 1x squared plus 0x plus 4. Don't forget you need to have all of the terms, all of the powers of x accounted for. So here 1, this becomes 2, 0 plus 2 is 2, 2 times 2 is 4, 4 plus 4 is 8, okay, which is our remainder. So this here is going to be equal to x plus 2 plus 8 over x minus 2. All right. So let's see if we can make sense of this. Well, if you take a look at, again, this remainder term, you have a constant remainder over a linear divisor. This whole expression will approach 0 as x gets larger. So if this portion approaches 0, it means this whole function should get closer and closer to x plus 2 as x approaches positive or negative infinity. And let's go back to our graph and see if that's indeed the case. Okay, so here, let's now graph y equals x plus 2. And we see that, there we go. Indeed, it's not going to be exactly equal to it, but it's getting closer and closer and closer. So it looks like not only can we justify that this function here is going to approach positive or negative infinity, we've justified that it does so by approaching a line, and we can actually determine the exact line. Okay, let's take a look at this one here. Like I said, we could use division, okay, but this is just, you're dividing by monomial, so we can easily just do x cubed over x, which is x squared, plus 1 over x. Look at that. We automatically have our quotient, which is a quadratic, plus our remainder term. And again, as x gets very, very large or very small, this is going to approach 0. So the whole function is not going to be equal to x squared, but it's going to be getting closer and closer to the function x squared. And let's check it out on our graph. So let's put this one here, and now let's sketch the graph of x squared. And look at that. As we zoom out, we see that they become almost indistinguishable from each other. Now, if we did zoom in, we would see that they're not exactly equal, but they're getting closer and closer to each other. So what this does now is it now adds even more precision to trying to determine characteristics of a function. Okay, so if we go back to what we had earlier, when we're dealing with these two scenarios, we have horizontal asymptotes, either at 0 or when the degrees are equal, a horizontal asymptote not at 0, which we can calculate. And now when the degree of the numerator is larger, we can not only determine that it's approaching positive or negative infinity, we can figure out exactly how it's approaching positive or negative infinity. Okay, so what I'd like you to do here is to determine the end behavior of this function here. You can even check to see if your answer is matches what you see on Desmos. Okay, and then we're going to head off to lesson 4. Okay, and for lesson 4, when we're eventually, our goal here is to get to sketch the graphs of rational functions, and as you can imagine, they're more complex than polynomials. And we're going to consider something that we only considered with respect to polynomials later on. Okay, this idea of the sign of the function. Okay, we're going to be very interested in trying to determine when these functions are positive or negative, and we'll see later on why that's going to be very useful to graphing. But one of the things we talked about when it came to polynomials is I asked the question, when can a function change sign? And what we came up with was that a function can change sign at an x-intercept, but it doesn't have to. So if you think of an order 2x intercept, it bounces off the x-axis. This is where it might change sign. What I want you to consider is, if we move away from those very nice polynomial functions, are there other places where a function can change sign? So that's the other thing that I want you to think about. Okay, so we'll give you 5, 6, or so minutes to work on that. All right, so we're back. So here, using this same idea, I'm going to divide these two and see what I get as a quotient. Now, by the way, because I have a cubic over a linear, I anticipate getting a quadratic. All right, so let's see what happens here. So I'm dividing by a linear divisor, so that makes life easier. 1, -5, 1, -3. I'm dividing by x minus 3. So 1, we got 3. This is going to be -2, -6, -7. And this is going to be, 1 minus 6 is -5. Sorry, and then here, -15. This is going to be -18. So this is going to be my remainder term, but I don't really care that much about it because I know this is going to be -18 over x minus 3. That's going to approach 0 as x gets very, very big. What I'm interested in is the quotient, which is x squared minus 2x minus 5. Okay, and what we seem to be claiming is that this is going to be what the function is going to approach as x gets very big or very small. So let's go have a look. So here's the function, okay, and now let's graph the parabola we got, and maybe we don't see it here, but again, if we zoom out, we start to see that this function is getting closer and closer to that parabola. And so what we say is that this function has quadratic asymptotic behavior, okay? Function like this here, we would say has, let's just go back, this has linear asymptotic behavior, and that line that it approaches is what we call a linear oblique asymptote. Now, I'll tell you right off the bat, most of the things you're going to be dealing with that have this type of asymptotic behavior are going to be linear oblique asymptotes. So you can see how this will be very helpful in drawing the graph and figuring out how this function behaves in the long run. So you have to imagine that if this is modeling some certain behavior, eventually this behavior will start to be linear as time goes on. All right, so let's go talk about that other question that I left you with, this idea of sine. So we know that a function can certainly change sign at an x-intercept. Okay, there you go. It can also not change sign at an x-intercept, as we've seen before. But now that we're looking at more complex functions, you hopefully realize that there are other places a function can change sign. For example, if you have a vertical asymptote, there you go. The function just went from positive to negative, yet there's no x-intercept there. Okay? You could also have, and I think we've referenced this before, you could have a jump. Okay? So you can change sign at a discontinuity. Speaking of discontinuities, you could have something that looks like it's crossing the x-axis, but what if you have a hole exactly at the x-axis? Well, the function is changing sign. Technically, there's no x-intercept here. Okay? Now, a jump is something we're going to see cannot happen with a rational function, but we certainly know that they can have vertical asymptotes, and we certainly know that they can have holes, and it could very well be that that hole happens to occur at the x-axis. So now, when we're looking for where a function can change sign, in other words, trying to figure out where it's positive and negative, we're going to have to expand our universe, okay, and not just consider x-intercepts. So what I want you to do is see if you can figure out when this function is positive or negative. Now think back to what we did when we had a polynomial. What was nice about polynomials is that they were easy to graph. So I see a third degree polynomial with a positive leading coefficient, and I know the x-intercepts at -1, 2, and 4. I know that the function is going to have to look like this, and I can just read the sign right off the graph. So it's negative from -infinity to -1, from 2 to 4, and positive from -1 to 2, and 4 to infinity. Problem is, rational functions are not easy to graph. So you're going to have to try to figure out how to easily determine when it's positive and negative without having to be able to draw the exact graph. But keep in mind what we talked about here. Think about where this could change sign. All right. And I'll give you a little hint. The idea of using a number line might still come into play. Okay. So talk amongst yourselves and see if you can come up with a strategy. And again, a strategy that's fairly easy and straightforward to determine when a rational function is positive and negative. So I'll give you maybe 3 minutes to work on that. All right, so we're back here, and let's see if we can come up with a strategy. So first thing I notice here is that there's an x-intercept at -1, and there's going to be vertical asymptotes at -3 and 4. These are the only places this function could possibly change signs. Okay, there's no holes, so there can't be one at the x-axis, and there's no jumps. So these are the only places. Well, let's use this idea, creating a number line. Similar to what we did before, except with our number line, we were able to sketch the graph of the polynomial over it to see when it was positive and negative. So here, let's put down the values at which it could change sign. Okay? But let's interpret what that means. That means that from -infinity to -3, there's no place for this function to change sign. So it has to have the same sign in this whole interval. Same thing from -3 to -1. If it's positive anywhere in this interval, it has to be positive everywhere. Similarly for negative. This interval here, it has to have the same sign throughout this whole interval. So the way in which we're going to easily determine the sign is say, well, hey, wait a minute. If it's going to have the same sign from -infinity all the way to -3, means I can pick any one number in this interval and test the sign of the function. If it's positive, it has to be positive everywhere. If it's negative, it's going to have to be negative everywhere. So let's take something easy. Let's take -4. Now notice here, because I have it in factored form, all I care about is the signs because I'm just multiplying and dividing. So I'm not even going to bother writing what -4 plus 1 is. I don't care. All I care about is that the numerator, -4 plus 1, -3, is still negative. And let's go to the denominator. -4 plus 3, well, that's still negative. And -4 minus 4 is again still negative. What happens when I multiply two negative numbers? I get a positive, and now I have a negative number divided by a positive number. That tells me in this whole interval from -infinity to -3, it has to be negative. This function must be negative. Let's do the same thing here. Let's pick -2. Okay, remember all I care about is the sign. -2 plus 1, still negative. -2 plus 3, positive. -2 minus 4, negative. So now I've got a negative number divided by, well, when I multiply these two things together, I get a negative number. So negative divided by negative, positive. Here, pick the easiest one there is, 0. 0 plus 1, positive. 0 plus 3, positive. 0 minus 4, negative. So now I've got a positive number over a negative number, negative. Lastly, let's pick 5. 5 plus 1 is positive. 5 plus 3 is positive. 5 minus 4 is positive. So I'm dividing a positive by a positive. It means it's positive in this whole interval. So here, where's the function positive? Well, it looks like it's positive from negative 3 to negative 1, and then from 4 to positive infinity. And where's it negative? Well, it's negative from negative infinity to negative 3, and then from negative 1 to 4. And this gives me an almost as easy way. Obviously, there's a bit of work to do, not quite as easy as a polynomial, but I use the fact that these are the only places where the function can change sign. So if I test one number in each of the intervals produced by these, I can determine the sign in those intervals. Okay? And now we've come to the point where I think we have enough information to start drawing reasonable sketches of these graphs. Okay? Keep in mind, we're not worrying about local maxima or minima or absolute maxima or minima. But what I want you to do is I want you to think back to all the characteristics we've been able to determine about rational functions and see if you can come up with an algorithm. So what strategy, what set of steps would you follow if you wanted to sketch a graph of this function? Now notice here, it's already in factored form, so some of the work's been done for you. Okay, I'm going to try to come up with a list of all the characteristics you can determine and then try to bring that onto the graph. Okay, so we'll give you about 10 minutes to work on that. All right, folks, so let's see if we can come up with a list of steps. Okay, so number one, well, you can determine the domain of the function, and essentially the domain is all real numbers except what makes the denominator 0. Okay, because we know that's the only issue one could have in a rational function. Okay, so we're going to say exclude x such that g of x, or I guess denominator, I guess I shouldn't use f at x and g of x since I'm using f at x for the whole thing. So let's say such that the denominator is equal to 0. Okay, now one thing that didn't come into play here, but I'm hoping you thought about, is you should simplify. Okay, and determine any holes if applicable. Now in this case here, this function was already simplified, but one thing we saw is that if you have something that makes, if you have the same expression, both numerator and denominator, it's not going to produce an x-intercept, it's not going to produce a vertical asymptote, it's going to produce a hole. So we always want that to be our first step, after determining the domain. So next, let's start thinking about what we saw the individual function tell us. Okay, find the x-intercepts. Oh, by the way, here, what is the domain? We might as well find it. Well, the domain is all real numbers except -3 and 4. So remember, we've seen this notation before. If I'm just excluding a couple of things, I can use it's all real numbers except these two elements, -3 and 4. The x-intercepts are where the numerator is equal to 0. And in this case here, our x-intercept is -1. Next, you can determine your vertical asymptotes. Here, this is where the denominator is equal to 0. Again, we're assuming that we've simplified already. So in this case here, our vertical asymptotes are, now this is where you need to be careful, vertical asymptote is a line. So you can't just say -3 and 4. It's x equals -3, that vertical line. X equals 4. All right? Next, determine your end behavior. Now here, the end behavior is very easy because the denominator has a larger degree than the numerator. So here, we know that the end behavior is just going to be horizontal asymptote of y equals 0. If the numerator had the higher degree, there would be, as we saw earlier, more work to be done. But determining the end behavior, now we have it. And lastly, and we'll see why this is important, or why it's going to be helpful, is to determine the sign of the function. Okay? Now, we've already done that up here, so I'm not going to repeat it. I'll just draw my line so that we can see it easily while we're drawing the graph. So it's negative, positive, negative, positive. And now we're going to put all these things together to draw the graph. All right? So I notice I have to go from -3 to 4. So I better make sure I've got room on my graph. So I'll put it just a little to the left. Okay. I'm not going to worry about the y-axis for now because we're not dealing with any local maxes and mins. And you're going to see that what I'm going to do is set up the structure of my graph. So what are the structure? Well, things that we know for sure. I know there's an x-intercept at -1. Okay. I know there's vertical asymptotes at -3 and at 1, 2, 3, 4. Okay. And I know the end behavior. Now, this is where we're going to see that the sign comes in really handy. Because here, I've got a vertical asymptote. I know I'm approaching 0. But is it doing so on the positive side or on the negative side? Okay. Is it approaching 0 from, again, positive side, negative side? Now, I know it can't cross the x-axis because there's no other x-intercepts. But look at that. I know that the function is negative in this whole region. So this function has no choice but to behave like this. And this is where the sign becomes very helpful. Here, I know that it's positive in this whole region. So this is going to have to go to positive infinity. Whereas in this area here, it has to be negative. So this is going to have to go to negative infinity. And similarly, it's positive beyond 4. So this has to go to positive infinity, and this has to approach 0 from the positive side. So without having to do any more work, I was able to get a good graph of this function. So let's go check on Desmos to see how well we did. All right, so let's have a look at this function here. Let's graph it. And when you look at the graph, you see that we came up with something very, very similar. Obviously, the exact shape might look a little different, but it's still pretty close. All right? So this is going to be the algorithm that we're going to use for curve sketching. I want you to show all of these steps each time. This one here was already simplified, so obviously there's nothing to show there. Okay, and think about setting up the structure of your graph before you actually start sketching the curve. All right, so you'll be practicing the 2 questions that come on the second page. All right, that's it for this one.